So far we've seen that benzene does not react like a typical alkene. If you put it in the presence of some activated electrophile like EY, the benzene will go after E and we'll get the formation of an activated sigma complex. And this is resonance stabilized, but it goes back to being aromatic by loss of a proton in a fast second step, which is going to give you the benzene ring back. So this is your typical reaction mechanism for electrophilic aromatic substitution. We can graph this on a reaction profile. We can see here that benzene is stable, the product is more stable, and we go through two steps, somewhat like an SN1 process, in which the electrophile adds to the pi system. We get the sigma complex as the intermediate species, and that then undergoes a fast acid-base reaction to produce ultimately the product. And this type of graph is going to be the same for each of the different electrophilic aromatic substitutions, regardless of what E happens to be. So we can start off by halogenating. We talked about the use of Br2, and we have to add a catalyst here because the benzene is not reactive enough on its own. And if this works, or if this happens, we're going to see the replacement of a hydrogen with a Br, and that then is electrophilic aromatic halogenation. So the mechanism looks like this. We could argue that the bromine is nucleophilic. It complexes with the Lewis acid FeBr3, and it gives us this complex. And this complex now is going to be attacked by the nucleophile. In the book, we see this equilibrium at the bottom in which maybe the bromine collapses to Br+. Sometimes you see this, sometimes you don't. I'm happy with either one of those interpretations. But what we've got set up now is a bromine which wants to be attacked. We've now got a much more electrophilic EY system. So the actual halogenation itself is the same as the typical mechanism we just saw. Nucleophilic attack of the benzene ring onto the halogen, and then loss of FeBr4, formation of the resonance stabilized carbocation, which you have to draw all those structures to show that this thing is stabilized, and then loss of finally the proton, where the FeBr4 minus comes in as a nucleophile, takes it off, and we end up with the bromobenzene product. So that's one of the 5 typical types of reaction that we have to worry about. The idea here now being we do not get addition, we actually get substitution, and that's what's going to happen for all these benzene systems. You can use chlorine as well, very similar mechanism that we discussed, and you can see now that we replace a hydrogen with a chlorine. That gives us chlorobenzene. Mechanistically, the halogenation mechanism fits exactly the EY idea, where E happens to be a halogen. Now, another example here, adding sulfonic acid residue, adding fuming sulfuric acid here. The mechanism involves attack on SO3, which is very electrophilic, and then through the typical mechanism, loss of a proton from the resonance stabilized intermediate, and that gives us the benzene sulfonic acid product, which will be useful later on. We can nitrate. This is very useful. It's a way of introducing nitrogen to systems. Here, HNO3 and H2SO4 are going to combine, and they're going to give us nitrobenzene. And add on to this, a useful reaction that's goes further, is to take a metal and some HCl and to reduce the nitro down to NH2, and that allows us to go from nitrobenzene to aniline, and aniline is very important in terms of being able to introduce nitrogen into pharmaceutical type compounds. So the mechanism for this, again, you need to know how to generate the electrophile. We've got nitric acid picking up a proton from sulfuric acid. It's a strange example of a very powerful acid being protonated by another very powerful acid, and we'll see now that we introduce a leaving group to the system. Water breaks off and we produce the nitronium ion, and the nitronium ion at the top right there is going to be very electrophilic. And we can see in the mechanism at the bottom again, we're going to attack that with a nucleophilic benzene. We're going to form a resonance stabilized sigma complex, which is then going to lose a proton to give us nitrobenzene. We talked about alkylation. Alkylations are problematic because we have the possibility of carbocations being formed, and carbocations can rearrange. So we'll see now that the typical process here does again require Lewis acid. The Lewis acid complexes to the halogen at the bottom, and if the carbocation is suitable, if the leaving group is able to break off and form a decent carbocation like a secondary or tertiary, it will. And you can see at the bottom here the secondary carbocation gets formed, and that becomes your electrophile in the electrophilic aromatic substitution process. We then get exactly the same type of mechanism. There's nothing different here. We just generated the E+, the electrophile, and we went after it with the benzene ring. We formed a sigma complex, and then we lost a proton to give us the alkylated benzene. Now that works fine if your carbocation is not the type that will rearrange. If you try this with a very simple primary system, like ethyl chloride here, you can get clean alkylations, and this is because the carbocation won't get formed because this is a primary system. So what will happen here is the Lewis acid complexes with the chloride, and you produce a very positive carbon where the chlorine is trying to break off. It won't because it would give a primary cation, but it is going to be reactive enough for the benzene to get interested and to go after it and to start the process. If we do this with a more complicated primary system, we tend to get mixtures. And this is because we're generating charge at a primary carbon. Even if it's delta plus, it's still not that stable. So we get these hydride shifts. As you can see at the bottom, if you start to put delta plus on the primary carbon, the hydride moves across in order to compensate for that, and the halogen is able to break off. And that hydride shift results in a secondary cation. So what you see at the top is a 1:2 mixture where the minor compound is that from the primary alkyl halide in which it hasn't rearranged, and the secondary product, the major product, is that of rearrangement. So this can be a bit unpredictable and not so useful. Other systems that don't undergo electrophilic aromatic substitution, halides here for example, you can't do this reaction on an sp2 carbon. So if your electrophile is sp2, it isn't going to happen. So the vinyl chloride at the top doesn't react, and the chlorobenzene at the bottom doesn't react. And you saw something about this last semester when you tried to do SN2 reactions on these types of systems, and they just don't work in the lab. Some reactions go too far, because if you put a T-butyl group on here, that T-butyl group is said to be activating. The electron donating ability of the alkyl group makes the benzene ring more nucleophilic in the product. And so the product becomes more reactive than the starter material. And since you haven't converted all the starter material to product yet, you have a competition between the product and the starter material for the reagent. And if the product is more reactive, it should react faster with the reagent. So you start to get over-alkylation, you start to get the reaction happening again. That can be useful if you're trying to do that, but it can be a problem if you're not. So here we've got two possibilities where we've over-alkylated in terms of putting one T-butyl group on, and then the second one has gone on because we can't control this reaction too well. Now, some problems with alkylation. If we have a nitro group, for example, on a benzene ring, that is electron withdrawing. That is going to make the benzene ring so much less reactive that it's not going to be interested in our electrophile. And so this doesn't work. If you're trying to alkylate a nitrobenzene with a Friedel-Crafts alkylation, it just isn't going to happen. If we take an alkene, we have an alternative way of making alkyl benzenes by protonating the double bond to make a carbocation, and then the benzene ring goes after it. So this is analogous to having a halogen attached, but instead of a leaving group coming off to form the carbocation, we have an alkene that gets protonated, giving a carbocation that then is going to react under the same mechanism that we saw previously. Now, what we need to worry about here is the possibility of using acyl group chemistry to give us alkyl products. Alkyl benzenes can be problematic in terms of their over-alkylation. If we introduce an acyl group, that can help, because the acyl group is deactivating. It pulls electrons away from the benzene ring, making the benzene ring less nucleophilic, and therefore the product is therefore less reactive than the benzene, and we tend to get monoacylation here. So the typical conditions are very similar to the Friedel-Crafts alkylation. We have an acyl halide at the bottom. We still need a Lewis acid to help drag this chloride off, and then we're left with an acyl benzene. This is a very powerful reaction. What we need to do here is understand again that the halogen complexes with AlCl3, the Lewis acid, and that gives us a complex which then collapses at the top, and you can see the formation of what's called an acylium ion. And this species is resonance stabilized, as you can see at the bottom, and it is a carbocation. It does not rearrange, that's one of the good things about this system, but it is a carbocation and it will still react in the benzene type chemistry in the same way a carbocation would. So mechanistically, generate your carbocation at the top. That's really the only difference here in this reaction, is understanding which the electrophile or what the electrophile is and where it comes from. And then you take the benzene as the nucleophile and away you go. You form the sigma complex, you get the resonance stabilized carbocation, which then loses the proton in the last step, and that gives you the acyl benzene. But the beauty of this reaction is that it's going to leave you with a product that is less reactive than what you started with, and therefore you're going to end up with that product completely. So what I've got here now is a add-on to that, where we saw NO2 reduced to NH2. Here we can reduce carbonyl down to CH2, and this is called the Clemmensen reduction. Here we have zinc, sometimes used as an amalgam with mercury, in the presence of HCl, and this removes carbonyls and gets rid of the oxygen and replaces it with a CH2 group. You can see now how this would be useful in terms of making clean alkyl halide, alkyl benzene products. If you start out with an acyl chloride and AlCl3, you're able to acylate the benzene to give the ketone at the bottom, and then you can get rid of the carbonyl by reducing it with zinc and HCl, and that's going to give you a clean product, the alkylated benzene, without any concern about rearranging. Now, once we've dealt with the 5 major products and reactions that we need to worry about here, which are halogenation, nitration, sulfonation, alkylation, and acylation, we can do what's more interesting and start putting the second group on. And we're going to have to be concerned about here about the characteristics of the first group that went on. Is the group electron donating, or is the group electron withdrawing? Because that will make a difference in how fast things happen next, and also where the next group goes. Is it the ortho position, the meta position, or the para position? So the first group that went on, in this case a methyl group, will serve as a guide. It'll serve like a traffic cop. It'll point in the right direction. You need to go over there when the next group comes in. So this experiment here is showing you the formation of a nitro-toluene derivative in which NO2 plus is the electrophile, and as you can see from the data at the bottom, you've got a large amount of what we call the ortho product, in which the NO2 group went next to the methyl. We have a very, very small amount, what we call a trace amount of the meta product, and we have a significant amount of the para substitution product. Now what you'll see here is a bit of statistics. You have 2 ortho positions and you only have 1 para position, so maybe you get twice as much of the ortho as you do of the para. But we really have to worry about how fast these things happen and also why we get these major products. You describe the ortho and the para as being major and the meta as being very much the minor. And there's a lot of sort of interesting background to this based on things like Markovnikov type ideas. So we often draw these types of pictures out where we're looking at the possibilities for each type of substitution. The top we have the ortho, middle we have the meta, bottom we have the para. And if we set this up to add to the ortho position, we can see some of the charge developing next to the methyl group. So you have the boxed in structure at the top, and that shows that some of the positive charge ends up next to the methyl. That's a good thing, because that methyl group will help stabilize by hyperconjugation. You can then draw the rest of the resonance structures. In each of these cases there will be 3 resonance structures, and you'll see for the ortho situation the charge can delocalize around the cycle, but some of it ends up next to the methyl. Likewise at the bottom of the para situation, add the nitro group at the para place, you end up with some charge at the meta position, but delocalization will put some of that charge next to the alkyl group for the picture in the box at the bottom. That is going to be stabilized again, more so than if that charge were elsewhere. So that does not happen for the meta situation in the middle. You cannot put any of that charge next to the alkyl group. So the alkyl group cannot help in terms of the stabilization of that carbocation. So the top situation is good, the middle situation is not so good, the bottom situation is good. And this is the argument for why we get most of the product being ortho and para. If you want to look at rates of reaction in terms of how fast things happen, well, we have 2 situations here which are quite fast, ortho and para, and we have the meta situation which is much slower. So you can imagine the situations on the left and the right are favored. There's a slight difference in the transition state energy for the ortho versus the para. The ortho is a little bit higher, and the argument there would be maybe some steric hindrance. As you're starting to put a group at the ortho position next to that methyl, maybe it's starting to clash, and maybe that's why that's a higher transition state. But again, you can see ortho and para are certainly favoured here. If we add a group such as methoxy and anisole, or methoxybenzene, we now have an added component. Not only will this group help with stabilization, maybe it'll help better or more by stabilization with the lone pair from the oxygen. So we can see here the diagram at the top is trying to show you the fact that this system actually has a dipole pulling away electron density towards the O, but that's through the sigma system. What we're concerned with here is delocalization of the electrons from the lone pair into the pi system of the benzene ring, and that's shown in the resonance structures at the bottom. So on the left, at the bottom, we can see the lone pair being pushed into the cycle, and you can see how that delocalizes through. And at the ortho positions, if we drew a resonance hybrid, the ortho position would certainly be delta negative on both sides. The para position would certainly be delta negative, but not the meta positions. So what's going to happen here is that those positions are more nucleophilic, ortho and para, and therefore chemistry will happen there faster. The outcome here is interesting because you take bromine with methoxybenzene or anisole, and you don't need a catalyst. This material is so reactive that it doesn't react with the doesn't need a catalyst. You don't actually need to put anything in here to make it react. So what we'll see now is that additional bromine, excess bromine, allows for the formation of this tribromide in quantitative yield. So this says now that the anisole is so reactive, it's activated by that methoxy group that you don't need a catalyst. But again, it's an ortho-para director. You can see at the bottom the outcome, mostly ortho and mostly para, very little if any of the meta product. Again, we'll argue about stabilization of carbocations in the ortho and para situations, but now you can see a switch. There is more para than ortho, and the argument you'd make there is the fact that with a methoxy group at the top, the ortho positions are becoming more blocked and more hindered, and so maybe the para position is favored. But the carbocation intermediates again will have similar properties in terms of their relative stabilization. We can see again, writing out these possibilities for the carbocations at the top, the ortho attack, you can put some positive charge next to that oxygen. You can't do that with the meta in the middle, but you can do it at the bottom with the para. So both the ortho and the para will have a fourth resonance structure in which the oxygen outside the ring can be involved in stabilizing the carbocation. That helps, and so that's why we go in the ortho and the para situations in those directions, and not so much in the meta. So these activating groups, groups that push electrons into the ring, are typically ortho-para directors. Again, we can see the graphs, very similar to what we saw before. Slight change in the relative heights of the ortho and the para situations because of steric environment, but a very similar trend in which those two are favored and the meta attack is not so much favored. Now, we switch this by going in the opposite direction. In this example, deactivating groups, for example nitro in nitrobenzene, not only is the dipole going in that direction towards the N, but the electrons from the benzene ring are going in that direction. This is pulling electron density out of the cycle, making the cycle less nucleophilic. It's going to make the next reaction slower, and it's going to have a different effect on where the next group goes. We'll say that these things are meta-directors. So at the bottom you can see the opposite from anisole. Anisole pushed electrons in, now we're pulling electrons out. So a very powerful electron withdrawing group such as nitro is able to pull electron density away from the cycle, and again those structures at the bottom show charge building up on certain carbons and not others, and if we drew a resonance hybrid for this system, you'd show the ortho and the para being delta plus. Now if this is to behave as a nucleophile, that's not good for the ortho and para situations because they're positive now. So the meta is the most nucleophilic of what's left of the three positions. So the experiment we see here, nitrobenzene itself, starting with a nitration, doing a second nitration, things change around. The ortho is minor, the meta is very much major, and the para is only a trace of the product. Again, if we worry about the possible carbocations, that will explain the outcome. So these pictures again showing the possibility for ortho, meta and para substitutions. At the top, the ortho product, the ortho possibility will build some charge up next to the nitro group. Now this is the opposite of where we were before. This is bad. You do not want that charge next to a positive group. And for any group that you put at that position which is delta positive, like a carbonyl or C triple bond N, they will destabilize a carbocation in the ortho substitution possibility. So we have that problem. Now in the middle, we don't have that problem. If you look at the resonance structures, the charge never goes next to the nitro group. That's what you want. At the bottom, you have the same problem as the ortho situation, in which some of the charge does go next to the nitro group, and therefore destabilizes that. So we have now the middle situation is, if you could say, the least worst. It's not as bad as the other two, and that's the preferred pathway. So take home from this is that deactivating groups slow the reaction down compared to benzene, and they destabilize cations in the ortho and para processes, but not so much in the meta processes. So meta is better by default. There's the graphs showing you again the shift in the possibility here for the different energies of the transition states. The ortho and para are destabilized compared to the meta, and the meta, even though it's slow compared to benzene, is still the best pathway here, and so we have a meta director. And that will, your job now is to work out what constitutes meta director, what constitutes an activator, what's a deactivator, and a lot of it's to do with the electronic characteristics of the group outside. Obviously strongly electron withdrawing groups tend to be meta directors and deactivating, and electron donating groups, typically those with alkyl groups or anything with a lone pair directly outside that ring, those systems will be activators, apart from the halogens. The halogens are the odd one out, and this is what we'll start with on Wednesday. Halogens have electronegative elements directly attached to the benzene ring. Through the single bond system, they are said to be deactivating, so that means they react slower than benzene. But they're the only one of the deactivators that actually give you ortho-para outcomes. And all of this is to do with the lone pairs on chlorine, or bromine or iodine. They can push into the cycle, very much like oxygen did for anisole, or N for NH2 could do in aniline. So they push electrons into the cycle. That makes the ring nucleophilic. It also stabilizes carbocations, as we did for alkyl groups. And what we'll do on Wednesday is spend time on that and try and work out that the exception to the rule isn't that difficult to understand.